different certain ages, they start to change things, or it's all just been the same?
Yeah, I mean, they do different activities depending on the season. So, like right now.
That clock is different from mine.
I've got 11:01.
You got 11:01. Yeah.
Morning. Can you hear me okay?
Yeah.
Okay. I wrote this down so I didn't forget anything. But I'm very excited to introduce Giselle Martinez as she gives her master's presentation. Giselle joined us 2 years ago, coming from San Antonio, Texas, to brave the Wisconsin winter. In May 2018, she earned her associate degree in liberal arts from Alamo Community College, then her Bachelor of Science in Meteorology with a math minor from the University of the Incarnate Word in December 2021. During her time there, she was very active in forecasting, and I heard she won a lot of their forecasting competitions. She earned an Excellence in Meteorology Research Award while there, participated as a member of the National Society of Leadership and Success, and even was able to maintain a Kokoro station throughout the pandemic, which I thought was really exciting. For those who aren't familiar with Kokoros, it's a volunteering, like put some instruments in your backyard, take some measurements, great. And she did all this while managing the challenges of remote learning during the pandemic. Her graduate school application as part of the AGU Bridge program stood out to me for many reasons, including her interest in convective systems and her desire to conduct mesoscale research in a collaborative research environment. So since joining us in fall 2022, she has pursued this path with curiosity, inspiring determination, and a contagious enthusiasm for Wisconsin's cold weather, which is amazing how much you've adapted to that. She has celebrated several major milestones in this last year in particular, including giving her first conference oral presentation in person at the AMS Tropical Meeting in California in May, in realizing her dream of visiting Colorado as she worked with scientists at NCAR to learn new analysis techniques in May, and becoming a US citizen, which is really exciting. We are excited to see what the future successes she has in store and where her research goes from here. So with that, Giselle, please take it away.
Thank you for the introduction. I'm really happy to see y'all here. There's a lot more than I expected. So thank you for coming. This is my research work of the 2 years that I've been here. We're going to be talking about the near-stored environmental moisture relative to the tropical deep convective growth using CPEX-CV Airborne data. So mesoscale convective systems are defined as a complex of thunderstorms that consist of convective and stratum-formed clouds, and they contribute to a large portion of precipitation and severe weather, especially in the tropics, such as a study by Galarno et al., who used satellite data, found that high frequency of those MCS occurring in tropical and subtropical regions, shown there in panel B. And one implication of these tropical MCSs is that they can serve as precursors for tropical cyclones, especially in those high frequency MCS genesis regions, including off the west coast of Africa or the tropical East Atlantic. We believe that it's important to understand the environmental conditions that support the initiation, growth, and sustainability of these tropical MCSs. And previous satellite and reanalysis-based literature deduced that moisture is a key parameter linked to MCS characteristics. One example is from Spiro et al. In 2020 that attributed greater precipitation rates with greater moisture throughout the free troposphere for both land and tropical oceanic MCSs, with main differences in precipitation rates to be observed around 800 to 700 hectopascals, that could imply there was a reduced dry air entrainment or enhanced buoyancy. Additionally, another study by Chen et al. In 2023 examined the pre-initiating low tropospheric moisture relative to tropical oceanic MCSs and characteristics such as lifetime and size. And their observations show that a pre-existing moist low tropospheric environment facilitates the initiation and growth of longer-lived tropical oceanic MCSs. So these studies establish a broad relationship between moisture and precipitation rate relative to land and tropical oceanic MCSs. However, another study by Chen et al. In 2017, who used radar and reanalysis data, implied that there is a vertical moisture variability on tropical MCS growth. For example, in panel A, here is showing a large precipitating MCSs in the eastern Pacific and the tropical East Atlantic when relative humidity, or RH, is above 90% in the lower levels, and the level RH is above 60%. And we see a decrease in those large precipitating MCSs in the tropical East Atlantic, but still pretty present when RH in the mid-levels is drier or below 50%. So this asserts there's a regional variability of tropical MCS growth with mid-level moisture variability. And that variability may be linked to the synoptic and mesoscale systems that occur here in the tropical East Atlantic. One of which is the African easterly wave, which are westward propagating systems that last from 3 to 5 days. They progress from continental Africa to the tropical East Atlantic, and they may serve as precursors for tropical cyclogenesis. So AEWs form along instabilities along the African easterly jet in continental Africa, and both can modulate the environment and convection in this region. For example, the jet can produce a shear enhanced environment, which could have implications on tropical MCS growth. And another component that is not shown in the figure is the Saharan air layer, or SAL, which contributes mid-level dry, dusty air that could impact the wave and the convection growth. But we are mostly focusing today on the moisture variability that is associated with the wave, in particular with the wave trough and the wave ridge. So many studies did emphasize the modulation of convection and environmental conditions relative to the wave phase, one of which was Janica and Thorncroft in 2016, that looked at those environmental conditions associated with convective activity linked to the wave and how they fluctuated from continental Africa to the West African coast and the tropical East Atlantic. And they noted that over the East Atlantic, moisture is enhanced within the trough and associated with more convective activity. So these observations do imply that there may be a two-way relationship where the wave trough can be supplying a favorable moist environment for the convection, and thus the convection is feeding latent heat from precipitation back into the AEW trough and intensifying the wave. So that couple system theory was actually explored in a recent framework by Mesoscale et al. In 2020, and that depicts a coupling system between a wave and an MCS as they progress through continental Africa to the tropical East Atlantic. And this figure shows a developing AEW coupled with an MCS moving in phase at the same speed, growing from a moist environment that was created by an intense jet and a strong monsoon trough as they move, to the tropical East Atlantic. Whereas a non-developing AEW with an MCS locates the convection south of the wave, moving faster, and that is more susceptible to mid-level dry air intrusion that leads to stronger downdrafts, cold pools, and faster propagation of the MCS. Thus, the MCS and the wave trough, when they're propagating fast together in phase, does promote wave growth, but also it promotes tropical cyclogenesis. However, The interaction between near storm environmental conditions and convective evolution, especially in this region, is not fully understood. And some limitations from literature include regional variability of moisture convection relationships, especially in the tropics, land versus ocean regimes, or just a focus on pre-initiating environments, but not how that environment evolves with convection. In addition, other studies using satellite and reanalysis-based data face difficulties in spatial and temporal resolution that may not capture that low-level environment correctly, or over and or underestimate rainfall in the tropics. In addition, the tropical East Atlantic is also a data-sparse region, yet there has been previous field campaigns in this region that paved a path of exploring convective evolution and the influence of those synoptic scale disturbances, such as the wave, the jet, and the Saharan air layer. And one of which was which was a ship stationed in aircraft-based field campaign from 50 years ago that took place in Dakar, Senegal, and looked at or investigated the small-scale tropical systems, effect on larger-scale circulations, and improved our understanding of tropical MCS structure, including stratiform precipitation and mesoscale up and down drafts. And airborne observations will improve from NAMA, which took place under 20 years ago in Cabo Verde, which had a goal of sampling the larger scale environment, including MCSs and the dust outbreak associated with those waves as they progress from the coast to the tropical East Atlantic. Their key findings was on MCS evolution with the waves, wave structure, tropical cyclogenesis, and dust influence on tropical convection. So these key findings from these field campaigns motivated the more recent NASA CPEX airborne field campaigns to understand these relationships further with more modern remote sensing capabilities. And one of those CPEX campaigns revisited the tropical East Atlantic with more instrumentation to examine the interaction between the convection and the environment. And that was NASA's CPEX-CV, and it operated in the Sal Islands in Cabo Verde from September 2022, and it had unique airborne instrumentation that was equipped in the DC-8, including a multi-frequency radar with a radiometer, a lidar for aerosols to capture dust, Doppler wind lidar, and launched dropsondes, all to sample the near storm environment, including high-resolution winds and moisture near the convective systems. CPEX-CV also had a total of 13 research flights near and away from the coast, with multiple passes in convective systems and sampling the near storm environment and also the wave environment. So this all leads us to the question we want to ask, or we want to answer. What is the relationship between the near storm environment and the convective growth in the tropical East Atlantic? And by using CPEX-CV airborne data, we hypothesized that greater near storm mid-level environmental moisture supports deep convective growth, especially when the convection is near the wave trough. So our hypothesis is actually based on previous literature, including the studies that I mentioned before, but also a recent study conducted by Ronan, Kirk, and Brown in 2024 that used similar instrumentation as in CPEX-CV for earlier CPEX and CPEX-AW campaigns. In their study, they examined dropsonde-derived environmental relative humidity and multiple vertical layers for multiple flights relative to the oceanic convection in the Gulf of Mexico and the Western Atlantic. And they suggested that organized systems do occur in moisture environments rather than isolated systems, but vary depending on vertical layers between and also within flights. So in each little box here in this plot shows that there is variability within the flights, but also with between the flights. So those results from their study In particular, that variability motivates our work to prioritize a flight in the tropical East Atlantic with an emphasis on that moisture-convection interactions that evolve with time. In our case is Research Flight 7, or RF7, that took place on September 16 of 2022 from 13 UTC to 1930 UTC. It was south of Cabo Verde Islands. This flight sampled a growing deep convection multiple times, as you see here in the satellite imagery, including its near storm environment and the corresponding wave environment. In addition, we see that as the flight is continuing back to Cabo Verde, this convective system continues to grow and persist even after the flight. So our work will revolve around why this convective system ultimately grew and what the near storm environment conditions look like to support that growth. So here we're looking at the larger scale environment in 7, and we noted that the convective system that will be sampled later in the afternoon was associated with AEW-6, and that's corroborated here with NASA portals. I emerged in a MET model for 700 hectopascals, relative humidity and streamlines for 14 UTC. That locates the convective system, the growing convective system on this moist side of a large-scale mid-level gradient, just ahead of the 700 hectopascal wave trough. So using that unique CPEX-CV Airborne dataset, we want to examine those environmental conditions that are associated with the wave and the growing convective system. Here we have the navigation track for 7, including a zoomed in image of the growing convection track. Each dropsonde, each circle was a launch dropsonde, in which there were 26 working dropsondes in this case that obtained metrics of relative humidity, vertical wind shear, cape and sin, and both the surrounding environment and near and within the growing convection. In addition, 7 also captured the environment behind and ahead of the growing convection, and this allows us to examine those environmental conditions from the dropsondes at different pressure levels. And we quantified those pressure levels from an example sounding, where mean layer environmental parameters at different pressure levels were used from a method from Verde, Kirk, and Brow, with a difference in the lowest flight level, which represents the flight level that was near and within the convective system during 7. And for our analysis, PVL and low level will be used interchangeably. In addition to dropsondes, we also used a unique remote sensing instrumentation that was provided by CPEX-CV, the first of which was Dawn, which is the Doppler wind lidar that measures wind by tracking aerosols at multiple sweeps at different angles to obtain vertical profiles of zonal and meridional winds. And one limitation of Dawn is that there would be no wind retrieval if there was no aerosols present. But in 7, the main issue was mid-level cloud attenuation, so we will have to keep that in mind for our analysis. Despite those limitations, we overlaid Dawn in vertical profiles from APR and Hamster to provide a unique wind data near the growing convection. The next instrumentation we use is the APR3, which is the multi-frequency radar that obtained vertical reflectivities of convective hydrometers using in a cross-track scanning method for KU and KA band reflectivity. In our analysis, we only focused on KU band because it best captures precipitation structure. And finally, we used Hamster, which is the microwave sounder that retrieves vertical profiles of water vapor and temperature. And we used Hamster to look at vertical profiles for relative humidity in the near storm environment, near and within the convective system. And we will start our analysis with Hamster RH with Dawn and dropsonde overlay. This is for 14 UTC to 1448 UTC, which is roughly the environmental leg that the convective system was propagating into. And this captures a layered moisture structure ahead of the convective system with a low moist level, but pockets of dry air aloft at around 50% to 60%. And that moist low level could be favorable for MCS initiation or growth, but we are not certain yet if that drier air aloft will limit that convective growth. In addition, Dawn also locates northeasterly flow with the moist low levels and easterly winds with the drier, relatively drier air aloft. However, we do see some attenuation from dawn, especially in the lower levels, from these mid-level clouds. So we will use some dropsondes that were launched throughout this leg, starting with 1404 to fill in the gap of the vertical profiles and look at the environmental conditions just ahead of the growing MCS. So starting with sounding from 1404 UTC, we noted a highly unstable environment ahead of the growing convective system with a moist low level with those northeasterly winds and a drier air aloft with those easterly winds associated with them. And still ahead of the growing convection or just northwest of the growing convection, we still note that very unstable environment, that moist level, and it's moistening slowly as DC8 is going into the moist side of a large scale gradient. And as DC8 continues flying southward, this is in the environment where the convective system is actually propagating straight into. We still note that the environment is pretty unstable. It's still pretty moist in the low levels, but with that drier air aloft. We also noted that the northeasterly winds in the low levels are weaker. So that environment that the growing convective system is moving into may be favorable for convective growth or convective initiation. So now we wanted to focus our analysis in how this layered moisture structure that we saw in Hamster RH and then in the soundings, and including the winds, are linked to the broader wave circulation, and we had to use aero-5 analysis to do that. So here we have on my left the dropsonde variable plots for PBL RH and 950 hectopascal winds, and mid-level RH for 700 hectopascal winds paired with spatial aero-5 RH and streamlines for 950 hectopascals and 700 hectopascals, all for 14 UTC on September 16th. And we noted that aero-5 does do a good job in capturing the flow pattern and the broad moist PVL and the mid-level moisture gradient compared to the observations from these dropsonde variable plots. So we will use aero-5 and reanalysis to provide a broader spatial and temporal context to our airborne observations. Additionally, aero-5 does capture the convection to be ahead of the 700 hectopascal wave. So now our analysis will focus back into the environmental conditions in the vicinity of this convective system. And we use APR3 with dawn and dropsonde overlay. This is for 17 UTC to 1750 UTC. This is the leg that captured the growing convection system, and that reveals the vertical structure of the growing convective system, including the south-southeast side and the north-northwest side. And NPR shows that the storm is stratiform precipitating, and it has embedded deep convection, but it also has a deep convective region or a strong updraft. And we also noted that there's possible new cells initiating just to the west of the growing system. And if you can recall, there is that unstable moist level environment just ahead of the growing convective system, and that may be favorable for those new cells that are initiating, regardless if there is drier air aloft. So then we also looked at Hamster RH just near the convective system. We did notice that there is a moisture structure in the south-southeast side, including greater moisture that was captured within that stratiform area, and a drier PBL to the west, which also may be influenced by the convection itself. But we also noticed that there is moistening aloft at around 2 to 5 kilometers in this northwest side. And that motivates us to look at these soundings that were dropped in this leg to see if we do see any indication of that moistening, starting with 1736 UTC. So the sounding at 1736 UTC also knows a pretty unstable environment. It's moist near the surface, but it's still pretty dry aloft. And that might have been influenced by some of the new cells that were forming in this region, but we know that the environment itself seems to be pretty favorable for set initiation. And 10 minutes later, at 1746, the DCA moved back into the system and still captures that unstable environment, moist near the surface, and drier air aloft. So that ultimately that drier air that we noted in the environmental leg seems to be moistening near the convection. Just to recap our CPEX-CV analysis, RF7 sampled a growing convective system and its near storm environment and the wave environment. The IR imagery shows growth of the convective system after the flight. The IPR3 captures the stratiform precipitating storm with embedded deep convection and just new cell initiating just ahead of it. Hamster RH also shows moistening aloft near the convection. And finally, the growing convective system was propagating west into an unstable moistening environment ahead of the 700 hectopascal wave trough. So how do these environmental conditions actually evolve with the convection with time, especially after and during the flight? And to answer this question, we needed an objective way to track the convection, its propagation, and intensity during and after the flight in 7. And by using that method, we can explore the environmental conditions and how they evolve with time after flying the convective system to determine if there was any convective growth. And we will be using Error 5 because we believe that it is capturing that broader moisture gradient, the flow pattern compared to the observations accurately. And finally, we will do all of this in the context of the MCS relative to the wave trough. So we use the TAMS algorithm for Mesoscale convective system, or TAMS, that was developed by Kelly Nunez-Ocasio and Zachary Moon, which use satellite and model data to track MCSs that satisfy the criteria shown here in this table, which is the cloud top temperature threshold at 235 Kelvin, the cloud top temperature cores, which are able to identify the deep convective cores within the clouds at 219 Kelvin, and a brightness temperature area at least or greater than 4,000 kilometers squared of embedded cold cores. If you want to learn more about TAMS, I highly suggest the QR code that leads you to the document or the preprint from Nunez-Ocasio and Moon 2024. Additionally, TAMS also tracks the identified MCS using an overlap normalization method. And basically what that means is that we use a cloud element at time t, looking forward at cloud element t plus 1, and use a mean overlap normalization method, and the code within TAMS will use that area or the overlap C to normalize and obtain a overlap percentage. And we had to adjust these settings based on the table and color here to have a consistent MCS track with only just one ID instead of multiple IDs for our growing convective system. And when we applied TAMS to our growing convective system, we were able to track it. It is identified as MCS 146, shown here in the plot, which now we will refer it to as MCS 146. It initiated on September 16th at 10 UTC, and it died, or dissipated, I would say it died, on September 17th at 15 UTC, roughly around 29 hours. TAMS also classifies it as a mesoscale convective complex, here are the small tables from the Mesoscale preprint that characterizes different organized systems or disorganized systems. But in our case, our system was actually organized, and that's this Mesoscale convective complex. So this is an IR-based satellite loop from September 16th at 12 UTC to next day, September 17th at 12 UTC, so 24 hours. It has an overlay AEW tracker from Lawson et al. 2022. And this shows the MCS or MCS-146 propagating ahead of and with the 700 hectopascal AEW center up until September 17 at 12 UTC, where it propagates just ahead and faster than the wave. And then after flying MCS-146, the near storm environment, which we can say that it was with favorable conditions for convective growth, we do see that there is a convective cell that formed just west of the convective system right here and merged with the convective system, or MCS-146. And so that full track, including the merge with that convective cell, will be what we will look at for our analysis moving forward. So now that we know that we can track MCS-146 using TAMs, we will bring back Aero-5 reanalysis to understand how those environmental conditions evolved with time, especially ahead of the convective system, during and after the flight, to determine why it ultimately grew. And we approach this by using a cone method. This is also from TAMS. We initially looked at the full cone, which is labeled here, which could be modified in size and angle, but our interest lies in the near cone to evaluate the environment the MCS-146 was propagating straight into. So each near cone averages Aero-5 environmental parameters, and they're linked to each MCS center, or the dark blue circles, and we will do this for a track starting from September 16th at 10 UTC, the initiation time, and ending it the next day at 0 UTC. And because our focus today is just on moisture, we will only be looking at Aero-5 specific humidity in the near cone. So from the area time series here for MCS-146, we did note that there was a steady growth in area during the flight, but we also note a rapid increase in that area when MCS-146 merged with that convective cell that just formed to just west of it. We also note that there was moistening with time in the specific humidity plot here for 10 UTC to 19 UTC. Especially in 970 hectopascal to 850 hectopascal. And this moistening could have been supported by that merge with the new convective cell that just formed ahead of it. And that links back to the relatively drier air that was captured in Hamster RH, which may indicate that this environment may have continued to moisten with time as the MCS was propagating west. We also note that there was a increase in max precipitation, and cold cores were getting colder both during and after the flight, which may have contributed to this moistening with time and suggests deep convective growth. But after the next day, 0 UTC, max precipitation does decrease steadily, and cold cores are beginning to get warmer. So we then looked at the conditions or the specific humidity plot for after 19 UTC to the next day, and we see that it was initially drying with time, but still maintains a moist environment. So we paired that with Aero-5 spatial plot for 850 hectopascal. This is for September 16 at 22 UTC. And this suggests that the near cone may have been capturing some of that drier air that's out ahead, maybe associated with the wave bridge, and suggesting that there may be an increase in propagation speed of MCS-146. Just to recap our TAMS analysis, MCS-146 is classified as a mesoscale convective complex. It lasted over a little bit, around 29 hours. Propagated ahead of and with the 700 hectopascal wave center, and then it propagated faster than the wave center, closer to dissipation. It also merged with the convective cell that just formed ahead of this MCS, and that may have been contributed to the growth in size that we saw previously in the time series. We also looked at the environmental conditions that evolved with time. We noted the mid-level moistening with time during the flight, the growth of the expansion of stratiform deck, which could be explained by the increase in max precipitation, intensification from the colder core pores, and finally MCS-146 did propagate into a drier environment associated with the ridge the next day, and that may have led to dissipation. And to support that key point, we looked at MCS wave relative speed for the full time span for MCS-146, and we noted that MCS-146 did become in phase with the wave at 17 UTC on September 16th, before it propagated slower than the wave, and then became in phase with the wave again the next day at 14 UTC and increased in propagation speed, and then it led to its dissipation. Yet the wave that was involved in this case actually regenerated another system that then became a Hurricane Ian a couple days later. So we're working with other colleagues to incorporate this analysis to their model to understand why that actually happened. And finally, this is just one CPEX-CV case out of the 13 in which the convection actually sustained, arguably from the greater mid-level moisture from our hypothesis. So that motivates us to look into another CPEX-CV case where DCA samples that growing convection multiple times, the near storm environment and the wave environment, again to test our hypothesis. And a brief overview of that other case, which is Research Flight 11. It took place 10 days later on September 26 in 2022. It was southeast of Cabo Verde. This flight sampled the growing convection multiple times, as labeled here, associated with the wave near the coast, and also earlier in the morning. So in the satellite imagery, we can see here DCA sampling that convective system multiple times. But what's fascinating about this case, it did not sustain after the flight. It sustained only a couple hours, maybe 2 or 3, before it eventually dissipated. So we want to investigate why. So we first looked at the environmental conditions that were relative to that MCS in 11, and we saw that there is also a mid-level moisture gradient where the growing convection that was sampled in RF11 was on this edge of a moist easterly environment and a drier west environment. But we will note that the growing convection was actually propagating into a more drier environment than the one in 7. And by doing that, we compared the environment for both cases, 7 and 11, using the statistical approach, starting with only PVL RH and mid-level RH for the entire flights for both cases, and that shows a drier environment for 11 throughout all vertical layers for the entire flight. In addition, we also did environmental only dropsondes, which are dropsondes that were launched ahead of the growing convection system in both cases with no convective influence, and we saw that for 11, again, there's a drier environment for the environment that was ahead of the growing convection, but especially in the mid-levels. So to conclude our presentation for today, our analysis used aircraft data, reanalysis, and the satellite MCS tracker, all to examine the near storm environment and those conditions that promote MCS growth. And we brought back our hypothesis of greater near storm mid-level environment moisture supporting the convective growth when that convection is near the wave trough. And observations in 7 noted that we did see a moistening with time above the low levels, confirming that there may have been greater near storm environmental moisture in this case that may have supported the growth of MCS 146, especially since it was near the AEW trough up until it dissipated a day later. However, in 11, we see the opposite of our hypothesis, where the convection was actually propagating into an environment with significantly drier air aloft. But in addition to that environment, other components that we did not show in this presentation, including the dust that may have been influenced in this case, coastal influence, lower Cape, and greater wind shear may have played a part as to why this growing convection in 11 did not sustain. So we believe that we must continue our analysis further by using a comparison of the environment with 7 and 11, but also including other parameters such as vertical wind shear, entrainment Cape, moisture convergence, and so forth. And we also wanted to use TAMS for the wave convection relationship in 11. That could bring some insight of what happened with the wave in 11 and the growing convection as well. And finally, we may have to consider the Saharan air layer for 11 since there was some dust influence in that growing convection. And finally, again, we will continue our analysis further in 7 after the flight, especially leading into its dissipation, with other colleagues to determine why it dissipated, but also why the waves were generated in another system that led to Hurricane Ian. And one of those methods we will use is MCS 146 eccentricity that looks at the structure of the convective system. For example, it tells us how circular or elongating that system was throughout its lifetime. Ultimately, we will continue our work with understanding the path of convective system growth in the tropical East Atlantic with consideration of other methods and cases. And before I let you guys go for your lunch, I just want to acknowledge some funding, NASA award and the Advanced Opportunity Fellowship that funded this project, and also my time here at UW-Madison. Don't worry, I'm still staying, so you won't get rid of me. I also want to thank NCAR's Centralized Visitor Programs for supporting that 2-week visit to Colorado to work with Kelly and Zach on TAMS personally. I had a blast. And some acknowledgments personally, my advisor, Angela Rao, my team members, Ian, Ben, and Anthony, who really were there every step of the way, giving me advice and really listening to me. That's all that matters. My committee, Myra and Angel, who not only gave me personal critique or anything like that, they also helped with this work. Some CPEX-CV colleagues, including Quentin and Alexis, previously from the University of Miami. They're not only extremely smart, but they're so kind and so funny, and it's always a pleasure to go and have a drink or dinner with them. Kelly and Zach for being gracious hosts in Colorado. I can't thank them enough for their hospitality, and I feel like I can consider them friends after the hike we took that took 2 hours. Friends and professors at and outside of AOS. There's so many of you, you know, Alex, Marissa, there's Allie, Nicola, there's Ruby, Clarissa, Jack. There's so many of you, and I really want to thank you for not only being here, but also supporting my time here. And I saw all of your presentations as well. You guys were great. And finally, my biggest supporters, my family, my parents, my sister, my brother-in-law, my niece, and my nephew, who are probably watching alongside my entire family, my aunts, my uncles, my grandma is probably watching too, knowing my mother. And of course, my cat. My lovely cat who turned 12 last month. And that's it. I will take any questions that you guys may have. Thank you.
We'll start with questions from students. What would you like to know? Steph, go ahead.
Hi, thanks for your talk. I am wondering, in your future work, you mentioned you're interested in looking at at entrainment. I was wondering, what are your ideas for kind of how you would do that? Are you looking at that from an observational perspective or more of a reanalysis perspective?
Yeah, so I've been thinking about this a lot. To incorporate reanalysis, the limitations of Error 5 really stand out to me, at least for my case, and I always wondered if I could use other reanalysis methods, especially with entrainment-Cabo, which I know very little about entrainment-Cabo, but I know some things about entrainment itself, and I feel like the comparison between 7 and 11, entrainment may have been detrimental for 11 than 7 because of the wind flow that I didn't really talk about here in this presentation, but the winds were drastically different in 11. So we might have to consider entrainment for 11 first and then apply it to 7 to see if there's any comparisons there or if it actually works. So right now it would be a good start to use reanalysis, but not just only Error 5. I would have to consider other reanalysis methods or data to compare with Error 5 to see if Error 5 is actually capturing it correctly or if it's under or overestimating something. Thank you for your question.
I'll just add one tiny piece of this based on a discussion last week that Giselle and I haven't talked about yet. There's a lot of ways you can try to calculate entrainment-Cabo given different models and estimates of vertical velocity and other things. I don't know if you were here during Brandon Woulding's. I know Larissa has like a lot of, we're gonna have a lot of discussions with Larissa on this, but Brandon Woulding, I don't know if you remember if he was here before, he has a plume model that tries to estimate entrainment through buoyancy, and so we're gonna try a couple of different methods to see if we can get a handle on that. So it's a tough problem. I'm glad you brought that up, and we have some ideas that I need to kind of talk to Giselle a little about that we're gonna explore. So thanks for that. Yep. Other student questions?
What made you decide to use TAMS for your tracking data set?
So I initially used TIMS from your work, and I don't know what brought it up. I think it was a meeting with our CPEX-CV colleagues. Kelly brought up the fact that we can use TIMS to track the MCSs, and it uses a different approach from TIMS. It uses satellite and modeling data, whereas TIMS, I really don't actually know how TIMS characterizes it yet. So we kind of shifted our focus to see if TAMS was actually following our MCS correctly, and compared it to TIMS, and we decided to use TAMS instead because we felt like it was capturing the full track. As I mentioned, we can adjust those settings, and it captured the full thing, whereas TIMS, it was capturing multiple MCSs. It was saying, okay, this is another cool core, this is another MCS, when that wasn't the case. It was probably multiple cores in the same convective system.
Yeah, I know Becky, you had some issues with like life cycle with TIMS, and so an actually interesting study is like how do the results change if you use TIMS versus TAMS, and that's a whole other big discussion that this was the best choice for our case, but a different case might have a different answer, right? Yeah. Yeah.
I have the code.
Another student question. We'll open it up broader. Yeah, Ian.
I'm curious with so much discussion on moisture. I'm curious on your thoughts on what the feedback your moisture is having on both precipitation and then the ice microphysics as well. I noticed there were a couple convective cores in your APR data that were not actually associated with rainfall, with rain, or rather ice, and I'm curious if you think that has any impact on the speed of your convective complex in RF7, as well as if there's any interplay with the AEW as well.
That could be a good thing to consider, since we don't really talk about a lot of the hydrometers involved. We do have other reflectivities involved, like we use just KU band here, but we also have K and W and vertical velocity. So I would have to look at those reflectivities to see if it captured any hydrometers. I'd probably do this analysis again to see if it had anything to do with the propagation of the MCS. This is kind of hard to say without analysis. but it could be a part. So that's why we wanted to continue it with further, with other environmental parameters, but also consider that maybe the MCS itself was its downfall or something like that.
Yeah, I know you didn't mention it because you didn't show it in this analysis, but you did it for a class project. There was a CAPS probe to get your crushable ice hydrometeors. So we got some in-situ data, but only at flight level. So there's a little bit of a discussion looking at some of the ice evolution in the context of the radar data. So that's kind of a separate question than I think what you're asking about how it might influence the change in the propagation later. And the hypothesis there is like to more of the entrainment of the drier air because it looked more like a squall line later on, which is a little, but I don't think thanks Giselle, the CAPS probe, I don't think it's going to give us all those answers, but it might help with some of our comparisons with the model. But does that get at, because there was like a couple questions there, does that get at what you're going for?
It's a loaded question, but yeah.
Yeah.
That gets at most of it.
Other questions? Larissa and John?
So you saw that growing or moisture was associated with growth, whereas dry air was associated with not sustaining. Do you understand why that was the case?
So generally, yes. When I was doing my work at undergrad, it would mean, if the air was too dry, then maybe the growth wouldn't sustain. Over the ocean, it's a little bit tricky. I had to throw away the general for this case because we did note that there is drier air, but we weren't really certain if that will limit the growth of this MCS. But then later, we noted that it did merge with another system, and that may have protected it in a way from drier entrainment, and maybe that drier air that we saw was moistening with time based on that merge, or maybe everything was just moving together. And it didn't help that the wave was actually just there and probably moistening the area as well. So when I mentioned the drier air aloft, it could have been in that time frame where I was capturing it by CPEX-CV, but then later it may have been moistening from the merge, the MCS itself, the wave. It's kind of hard to know. It's kind of hard to pinpoint. But in this case, I don't think it was a detriment for the MCS. So that's why I wanted to look at 11 to see why that one didn't sustain, because it was significantly drier. To see if there is some correlation to your question.
So do you understand in general why dry air versus moist air has an impact? Do you just want to say that for
entrainment,
the audience? Entrainment, yeah.
Entrainment, and that's why we want to look at entrainment cape, because I feel like that's a better method over the tropics. It's kind of easy to say, it's more unstable and stuff like that, but over the ocean it's a little bit tricky to say that cape was the only instability and the factor that made it grow. But entrainment is a big part, at least for 11. We don't know yet for 7.
John and Myra?
Yeah, very interesting, Giselle. Great work. Forgive me for my naivete. The proximity of your MCS to the wave, is that the same in both research flights 7 and 11?
No.
Okay, so
Yeah.
can I follow up then? Because is it possible that the proximity to the wave axis in research flight 7 provides at least enough forcing that a little bit of mid-level dry air, which is going to be packaged as potential instability there, is not overwhelmingly a hindrance to convective activity? Whereas if you're away from the wave and you don't get any forcing to lift the whole call broadly, you're really going to depend on what the stratification is in terms of moisture. Is that a reasonable way to think about this?
Yes, exactly. Actually, we looked at some methods. We didn't talk about it here, but one of the more recent frameworks was like the marsupial pouch theory, where if the MCS is within the AEW circulation, we didn't see a circulation here, but if it is, it's protected from that outside environmental entrainment or anything that can become a detriment. But if it is in the vicinity of the wave allows for that forcing, which we don't really see a lot over the ocean compared to land, where land, there's temperature gradients, there's the jet also that allows that forcing. But over the ocean, it's a little bit more nuanced, and I would say the wave was that forcing. ascent, and it may have protected our MCS. And as the MCS became larger, it was becoming more protected from that outside surrounding air until it reached the ridge, where
Yeah,
you know,
okay.
the ridge kind of messed with the mechanism for the wave.
Yeah, well, then you have no longer any forcing for ascent, and so you
Exactly.
depend entirely on what you get from your convective modes. Right?
And another thing that I didn't mention was that aside from this convective system, which was the largest, there's other convective systems surrounding the wave. So the wave would be like right here, the wave trough.
Okay.
And there's like this one was decaying already. These, I don't really know if they lasted as long, but they initiated at this time. And there's one behind this convective system, there's one ahead of it.
Okay.
So there's other convective systems that were initiating surrounding the wave trough. But I feel like MCS 146 was at least in the perfect spot relative to the wave up until it reached the wave ridge.
Okay, and then can I ask one more question?
Mhm.
I'm really intrigued by the shape parameter, and especially your last slide on your future work, or close to your future work slide, where you go from really high ellipticity, or low ellipticity to fairly high, so it gets elongated.
Yeah.
What is going on in the environment as 146 heads into an environment that elongates it? Is there stronger deformative strain, and does that mean that the wave is no longer so potent and so on? I mean, are those all related?
It could be, because it does become very elongated. It also propagates faster than the wave, and
Okay.
it just leaves the way behind.
It finds its way away from it, okay.
Exactly.
Okay.
So once it reaches a point where it becomes in phase around like 14 UTC with the wave, and then it wraps up in speed. And
Okay.
we don't know where that is yet, but from satellite we noted that it does.
Okay.
At least from the wave center.
Okay.
And then when it propagates faster, it's reaching a drier environment where the ridge is, and then it becomes more linear.
Yeah.
So other work from our colleagues are actually trying to figure out if it's drier entrainment, which causes it to become more linear
Yeah.
and eventually dissipated. But then how did the wave regenerate another system that eventually led to hurricane?
Yeah.
That's the part that's just, I don't know, it's really confusing because this would suggest that the wave was actually weakening
Yeah.
with that couple system theory.
And
But it seems like that was not the case.
And of course, the bias I bring to such an observation is that in the mid-latitudes, when you have a circular vortex structure and you stretch it into a line,
Mhm.
it's no longer cyclogenetically potent. It dissipates. It's completely out of the game. And it sounds like there's some element of that here, except that then you get the mystery about where does EN come from, which is really interesting.
That's fascinating about the tropics, truly. A step further from where I was just looking at dry lines in Texas.
Yeah.
So it's really a mystery. So that's why we're actually working on that, exactly what you mentioned. If the wave really did have a bigger part here, and it seems like it should have, because it didn't weaken when the system was elongated, possibly from dry lines. We don't know yet.
Really interesting.
Myra? And then I'll have to go back to the Myra's next.
So,
There's
yeah.
a money question too.
Okay.
Actually, part of my question related to John's question, except that I phrased it differently, because in many of your slides, especially at the beginning, you talked about the environment of the storm. So what do you guys define as the environment of the storm? Because it's going to obviously have an influence on what is surrounding, what you're actually taking into consideration for your analysis. So actually, with that in mind, I'm just gonna go ahead and ask the specific question that I wanna ask. Thinking about the environment of the storm, you're planning on comparing this RF Flight 7 with R11. And you mentioned dust was probably the reason why RF11 didn't develop as it should have. But there's dust in the environment of RF7 as well. So do you wanna talk a little bit more about that?
Yeah, there is dust in 7 as well. The dustier region is,
It's actually a lot.
it is a lot. So the dustier region would be where that dry level gradient is, right here. So it was dust that was surrounding this area, the MCS is right here. So in the beginning, when I was doing my analysis with this case, we would always say that it was a dustier northwest environment, but it never really reached the convective system, or maybe, again, it was being protected by some background dust that was involved. but I'm not really too sure. So the comparison between the dust with 7 and 11 would be interesting, because I'm not really too sure if it was also part of why 11 didn't sustain, but I just know that it was dustier than 7. But there was also dust in this case as well.
So Dave and then Angel, and then with the time, we'll move questions to later, yeah.
So one thing in relation to the time the tropics now, I guess this is what we find more in the Pacific, is that when you compare large MCSs during El Nino versus La Nina, a big difference that you find is, like you said, the environment is a little bit better. But actually that stretched humidity that you get in vertical and then upper levels is actually there well before the MCS even exists. And so you actually have a period of convection, deep convection, that almost precursors to the organized MCSs. Do you see a similar thing here where you're almost getting a preconditioning of the mid and upper levels that are helping actually sustain an MCS longer? Kind of similar to what we see with El Niños.
El Nino and La Nina, that's my mom's favorite topic to talk to me about. That's a good question. If I'm understanding it correctly, you mean the pre-initiating environment in which this one grew?
Yeah, so ahead of the MCS, do you actually see like convection that would actually be helping sustain and increase the humidity of the levels?
That is also something that I didn't note in my picture work. I would like to look at the pre-initiating environment before anything like that even happened. I mentioned the other convective systems in the vicinity of the wave, but what exactly led it to created that moisture gradient, if that makes sense?
Yeah.
Like what exactly happened? Like was it an MCS or was it the wave? Was it something? And I don't really know what preconditioned the environment yet, but it would be a good thing to explore, especially with aeroflight but other reanalysis and maybe some modeling, to look at how it became a moisture gradient. And we're arguing that the moisture gradient, the moist side, is actually sustaining this MCS. Other factors are as well. It grew very quickly and then it dissipated. So that's a good question.
Yeah, Angel, then we'll call it.
Right. I have a comment and then I'll ask you a question. So I just want to clarify a little bit about like the axis of the wave and the potential role of the MCSs, going back to John's question. So when you have in the wave, you have the trough, and then to the east you have southerlies, and then to the west you have northerlies because you're embedded in easterly flow. So in accordance to like the dynamics of like easterly waves, and in accordance to the stuff that we're working on, the southerly flow is actually not where you would expect to have the most moisture, because that's where most of the moisture is actually being affected from the ATCC. So the pouch of high moisture is actually more closely located to the trough axis, which is where you're seeing a lot of your MCSs. So in general, you're not necessarily going to expect to see a huge reservoir of moisture in the southerlies where you're seeing maybe that second case. And of course, when you're seeing the northerlies, you're getting an advection of dry air in. So it makes sense that that's actually corresponding to the decay of the MCSs. And this is actually corresponding to what Kelly's framework is with the CPs. And of course, you probably know this. I'm just saying this to just clarify some of the questions that we're talking about. This is actually really closely related to the work that I did as a postdoc and the stuff that I've been working on with Victor since we've been here. So we should talk more about this off the grid. But the question that I have for you is like, so if we go back to your slide about your hypothesis and the answers that you've had, I'm actually quite intrigued of what you think of this hypothesis moving forward. Would you still stick with it, or do you think you would change your hypothesis slightly as you're doing more work on this?
Last night when I was trying to go to sleep, I made more hypotheses based on this hypothesis. One of them was well, okay, greater near storm and environmental moisture. What about the low levels? What about the upper levels? What about the deep layer? And how does that play a part in this hypothesis alone? Because we didn't look at the upper or deep layer that much. We only say, okay, it's a moist low level, sure. But then I also note that the PBL was getting drier at some point, and in our TAM's specific humidity plots, which I didn't mention, the PBL is also getting drier here. Some soundings, the PBL is also getting drier, and that, I don't want to say cold pools, but it might have some influence from the convection itself. So My hypothesis will grow. I still believe that moisture is a main component. Where it is, with vertical profiles, maybe that will change. But I do believe that there is some growth, there is some relationship between growth of the convection with the wave trough. But then, we have the moisture, we have the wind shear, we have entrainment gate. That might change the hypothesis a little bit more. It might extend it really, really, really long. Maybe it will branch out, but I try not to in this presentation. But for now, I think it's correct to some degree for 7, not for 11, at least not right now. But I do believe that the deep convective growth and the AEW trough are linked. Whether or not that relates to the near storm mid-level moisture, I don't know. But that's a good question. It would have to be more analysis of all vertical layers to see how they change with time. So we only saw from the surface to 700, and we kept it at that. So it would be fascinating to see what the environment looked like above 700, and if we see that in both cases.
Cool, awesome, great work,
Yeah.
and look forward to chatting with you.
We look forward to
Yeah,
some
we
more
need to start
discussions
doing
with this. Congratulations, thanks. I'm sorry, I know you said there was an online question.
I'll forward it.
Yeah,
Great work.